Welcome back to the lesson on the derivative of a function. We just explored the derivative of x to the power of n and discovered that f prime x, or the derivative of x to the power of n, equals n. So that means that the power will become a coefficient, will come in front of x stays the same, and then the exponent of x from n becomes n minus 1, so is reduced by 1. We use this formula to differentiate all polynomial functions because polynomial functions are basically a bunch of terms in the form x to the power of n, sometimes with a coefficient in front of them. So either added or subtracted to each other. But we can basically use this formula to differentiate any function or non-function that has the terms expressed in power form. This is what we call the power rule in differentiation. Before we look at our examples here, I want to bring your attention to some simpler examples or simpler terms that will help us differentiate bigger functions a lot faster. So first, we'll start off with differentiating x to the power of 5. So the derivative of x to the power of 5 would be equal to, remember that the power of 5 will become a coefficient now. So 5 comes in the front, x stays the same, and the exponent from 5 will reduce by 1 to make this 5x to the power of 4. So try one more. If we have x to the power of 17, want to differentiate, that means that would be 17x to the power of 17 minus 1, which is 17x to the power of 16. Now, I bet you can do this a lot faster. So if you have x to the power of 9, you can say that the derivative is 9x to the power of 8. So let's move on to another one. We have x to the power of negative 4. We want to differentiate this. So that means that we're taking negative 4 to the front of x, becomes a coefficient. Then the power of x from negative 4 will reduce by 1. So this will be negative 4x to the power negative 5. I hope you can see the reason why I took an example with negative powers. So be very careful when you reduce a negative number, you're getting even a bigger negative. It's a common mistake and very easy mistake to make. So let's do another one. Try this on your own. So if you have x to the power of negative 13, so the derivative will be equal to negative 13 x to negative 14. Now let's take a look at another one. This time we have 7x to the power of 5. We're differentiating this. Now this is the multiplication of the constant 7 by x to the power 5. The constant is not differentiated, it will stay intact. So we only differentiate the variable part, the x to the power of 5. So that would be 5x to the power of 4. Simplify. 7 times 5 is 35x to the power of 4. So next we'll take a look at another interesting derivative. This time we have the derivative of 8 times x. So again, the coefficient will stay the same, intact, and we are differentiating only x to the power of 1. So that means that the power of 1 will become the coefficient, x stays the same, and then the power of 1 is reduced by 1. So that would make it 8 times 1 times x to the power of 0. Now, x to the power of 0, remember 1 minus 1 is 0 here, right? Would be equal to 1. So this is basically 8 times 1 times 1, or simply 8. So as you can see, the derivative of 8x is 8. And I want you to think, why is that? Remember that 8x is a linear term. So the rate of change of the function y equals 8x is also, or is indicated by the slope of the function. So the slope is a coefficient of x, and that's the reason why the rate of change of the term 8x would equal the slope or the coefficient. Let's do one more. If we have negative 7x, we'll say the derivative would be equal to simply negative 7. Now, let's take a look at another interesting example. This time we have the term 3. We want to differentiate this. So as you can see here, there is no x in it. So what I'm going to do is change this expression a little bit. So instead of having no x at all, I'm going to write x to the power of 0, which is practically 1. And 3 times 1 is still 3. So we're differentiating this. So what that means is that now we have 3. That's a coefficient that doesn't change. The power of 0 will become the coefficient of x. And then we have x. And then we have 0 minus 1. So let's simplify this. We have 3 times 0 times x to the power negative 1, which would be equal to 0. So we're going to say that the derivative of a constant number will always be equal to 0. So when you think about it, the reason why the derivative of a constant number is equal to 0 is because if we were to draw the graph of a constant term or a constant function, for example, y equals 3, 1, 2, 3, right here. Let's scale it because why not? Now the derivative means rate of change, or how fast the y values are changing. So if you were to describe how fast the y values are changing in this line, that means that you have to find delta y over delta x, or the slope. So the steepness of this line is 0. Delta y over delta x is 0 because the y values are not changing regardless of what x values become. And when a quantity doesn't change, the rate of change, or the derivative, or the speed of change of y values, or the slope of the tangent would be equal to 0. So whenever we see a constant in a polynomial expression that we're trying to differentiate, we'll say that the derivative of it would be 0. Now let's get started with our examples. Let's change the color here. So f prime x equals, we have number 7 become a coefficient, and then x, the power of 7 will reduce by 1, and that will give 7x to the power of 6. Obviously, we can do this a lot faster. So for g prime x, we'll have number 15 will stay intact as is. And then we'll differentiate x to the 100, which is basically 100x to the power 1 less than 100, 99. And then minus, we have 3. Differentiate x to the 12, that's 12x to the power of 11. And then plus 5x, this is a linear term. We know right away what to write in here. So just write 5. No need to show how you reduce the powers. And here we have a constant term, and the derivative of a constant is 0. You may write 0. You may as well write nothing at all. And I will write nothing. And that the next step, you simply simplify every term. So we have 1500x to the power of 99, and then minus 36x to the power of 11, and then plus 5. And that would be the derivative g prime x. Now let's move again to another example. This time we have function kx equals 2x to the power 6 minus 7x to the power of negative 6. So here we go. We are finding k prime x equals, number 2 stays the same. Differentiate x to the power 6. That makes 6x to the power of 5. And then minus 7. That stays the same. Negative 6 becomes the coefficient. And then x. Negative 6 minus 1, negative 7. And now we simplify. We have 12x to the power of 5. Minus 2 minuses will make a plus, 42x to the power of negative 7. This is k prime x. However, when you think about it, in the past we've mentioned that an answer is considered to be in unsimplified form if the exponent is still negative. So one way of fixing this will be by bringing x to the negative 7 down in the denominator and making it positive. But very often, you will be asked to write the final answer in the most simplified factored form and with positive exponents. Now, most simplified entails that the powers have to be positive. In factored form means that we have to make the powers positive by factoring the negative powers. So let's take a look how we do this. So we will be taking out the greatest common factor from the two terms. I'll start off with the coefficient part. So 12 and 42 have in common the factor of 6. Now x to the 5 and x to negative 7 will have x in common. And the power we can take out is the smallest power. As an example, I will bring in here x to the power of 2 minus x to the power of 5. So when we find the greatest common factor, that would be x, smallest exponent, and that would give 1 minus x to the power 3. So from 5, we take away the two powers that we have factored. So when we look at our expression here, the smallest power we see is negative 7. So that means x to the negative 7 is the greatest common factor. And from 12, once you take 6 out, we have 2n. And then for x, once we take negative 7 out, we're going to have 5 take away the negative 7, which we have factored. And then plus 42 over 6 is a 7. X to the negative 7 is all out. And now we'll simplify a little bit more. So we have 6x to the negative 7. 2x to the power of 5 minus negative 7, that's a 12. And then plus 7. So we have one more term that we need to express with positive powers. That has to come down in the denominator. 6 will stay n. We have 2x to the power of 12 plus 7. And in the denominator, we'll have x to the power of 7. And that's k prime x. So next we're moving on to example number 4. So this looks like a beast equation. And that's not Mr. Beast, by the way. Goodness, how do I know all these things? I don't know. So as you can see here, we have lots of radicals. And that's what makes this a little bit awkward and complicated, or look complicated. It's actually pretty simple. We know that radicals are nothing but powers. Recall that if we have the nth root of some number a to the power of m, that would equal a to the power of m divided by n. So step number 1 will convert all the terms into powers, from radicals to powers. Root of x is x to the 1/2 plus 9. Third root of x to the power of 7 would be 7 over 3 here. And then minus 2. Now you see that down here we have x squared 5th root. That means that would be x to the power of 2 over 5. But we also want to bring it to the numerator, so we can write the term in power form. And that will change the power to negative. So as you can see now, we have power terms throughout the equation. So we'll start differentiating. Now you write t prime x. So all we did in the previous step was rewrite the same equation differently. So the derivative would be 1/2 of x to the power of 1/2 minus 1. I'm going to show the steps in here because we're dealing with fractions. It's our first example. You learn how to do this faster with practice, always. So derivative of x to the 7 over 3, that's 7 over 3, x to the power 7 over 3 minus 1, minus 2 times. Derivative of x to the negative 2 over 5 would be negative 2 over 5, x to the power negative 2 over 5 minus 1. So let's see how this simplifies. So we have 1 over 2. Now x will be to the power of, so you see how you have 1 over 2 here minus 1? So that's the same as minus 2 over 2. So you want to have same denominator. That will make it negative 1/2. Obviously you can use a calculator, but whenever given a chance, use mental math. It's a good exercise for the brain. So the 9 and the 3 will simplify to a 3, so times 7, 21. X will be to the power of, same idea, 7 over 3 minus 3 over 3 this time, that's 4 over 3. And then minus, oh, wait a second, minus and minus will make a plus, so that's plus 4 over 5. So we'll write that. And then x will be to the power of negative 2 over 5 minus, we'll write 1 as 5 over 5, so negative 7 over 5. All right, party time. We are going to write this again in factored and most simplified form. So we need to take out the greatest common factor. And it is in our best interest to take out the denominators in here. You see that the coefficients are very interesting in a way. They're fractions, right? So when you take out the denominators, as you can see, you have two different denominators. They don't have anything in common, so we have to take the lowest common multiple of them out. So that will make 1 over 10. So as you can see, we have x appear everywhere in every term, so x is common as well. And we are taking out the smallest power, so that's a negative 0.5. That's 1 1/3. That's negative 7 over 5, so that's even more than negative 1. So that means that that's our smallest power, which is coming out. And now we'll have to multiply by whatever is left out of the terms. Now, when you're writing a test, obviously, go ahead and use a calculator, but remember how we figure out the coefficients left in the expression. So if you have 2x minus 6, you take 2 out, it means that 6 will be multiplied by, divided by whatever you took out. So that means 1 over 2 must be divided by 1 over 10 that we took out. So 1 over 2 divided by 1 over 10, remember, would be 1 over 2 times 10 over 1. So that makes it a 5. So 5 is the new coefficient of the first term. Then we have x. Power negative half, take away the power that is factored, which is negative 7 over 5. And then plus. We took 1/10 out of 21. That means that 21 divided by 1/10, 210. X will be to the power of 4 over 3 minus negative 7 over 5. And lastly, we have 1 over 2 out of 4 over 5, which means 4 over 5 divided by 1 over 2 will be 4 over 5 times 2 over 1. That's 8 over 5. Sorry, where are we going here? So 4 over 5 divided by 1 over 10 would be equal to 4 over 5 times 10 over 1. So that would be 10 over 5 equals 2. So that's an 8. X to the negative 7 over 5 is all out. So we have a little bit more work to do here. I'm going to write a long fraction line. So I will bring 10 in the denominator, that's where it is. And since x to the negative 7 over 5 is in the numerator, I'll bring it down so that the power becomes positive. Now let's take a look at our numerator. We have a 5, we have x, so negative half minus negative 7 over 5, that means negative half plus 7 over 5. Or should we say, if we want to get the same denominator, so we need to make this about 10. And you can use the calculator to evaluate this a little bit more quickly. But practically, that's what you do on the test. Again, as always, try to use the mental math in here. This will end up being 9 over 10. I don't want to go through the entire process of adding and subtracting fractions. That's not the point in this lesson. Then plus 210, we have x, and this time we have 4 over 3 plus 7 over 5. And in fraction form, exact form is 41 over 15. And then plus 8. And this would be the most simplified form of the derivative of the function tx. Now let's move on to the next example, 5. This is very straightforward. I chose this example because the powers are irrational numbers. And that can be a little bit questionable when it comes to differentiating. It's very straightforward. So bring pi as a coefficient and write pi minus 1 as a power. So do not subtract. We cannot simplify or round the answers when they are in the power. So we cannot round the powers. And the same thing with the next term. So minus root 2x to the power root 2 minus 1. That's as simplified as it can be. So next, we have an example in Leibniz notation. So remember that ddu means simply the derivative. So you can look at it as u8 prime. So if this is easier to you. So that means that the derivative here would be 8u to the power of 7. So these are the main examples I wanted to go over to practice the power rule. In the next video, we'll look into finding the equation of a line using derivatives. Thank you for watching, and I hope this made sense. Bye for now.